Okay, so welcome back, everybody. All right. So last time I'd started discussing parametric surfaces, or at least I'd hinted that that was what we were about to do. So if we go back for a second to the picture of the plane, uh, as I mentioned last time, if I want to discuss a curve, like discussing this is easy based on what we've done, or what you've done now for like 10 years or something. Being able to describe this as a graph of a function, so that's easy. But if the curve that I want to do analysis on looks something like this instead, that's a little bit more complicated, right? And so to address that, we labeled a point here as a vector, but it's a vector that changes with respect to some parameter t. So we call this r of t, which we labeled as a function x of t in the I slot plus y of t in the j slot. Or if you don't like ij notation, we would say that this thing had an x and y slot determined by those two functions like this. So anyway, this is how we dealt with curves that look like this. And this was the notion of a parametric curve, right? Um, Okay, and if we move this picture to space, then we could similarly do something like this. So if we have a curve now that is not something very simple like a line or just some normal piece of string, maybe that doesn't pass over and under itself here, I could have a curve in space, but maybe the curve, kind of passes over and under itself in a way, so maybe it looks kind of like a knot. And some of these are, directly above each other, right? And so we found that the best way to describe this kind of thing here was as a parametric curve in space, which we did very similarly to the plane here, where a point on this curve, so we'll say here, right? This was determined by a vector. We thought of this vector as moving and tracing out this curve, right? And of course, we viewed that as this vector valued function. Um, R of t is x of t I plus y of t j plus z of t k, right? And t, your parameter, lives in some window, right? So maybe your t was for, maybe your t was for, it lived in just the reals, so t could be anything. And in that case, maybe you had some curve that was infinitely long. It went all over the place, right? So if you had like a line, for instance, right? If you had a line and not just a piece of that line, then maybe t would live in all the reals. But typically t was in some closed interval ab. Same thing was true here, right? So t was in some closed interval ab. And I stressed over and over again how if you wrote out a parameterization of a line in the plane or in space, you weren't finished until you tell me where that parameter lives, right? Because you can have a curve that looks different based on where the parameter lives, right? So the simplest example of that, and kind of the one of the first examples of a parametric curve that we discussed, was a circle. And so going back here, what if I have two curves? Okay, so the first one is cosine t plus, so cosine t I plus sine t j, where t is the, so we'll say that the parameter lives from pi to 3 pi over 2. And we have another parameterization, which the actual form of the parameterization is exactly the same, but my t lives from 0 to pi over 2. All right. Well, the two curves traced out by this, right, they are part of the same larger curve, but taken as, their own curves, right? This curve c sub 1 and c sub 2 associated to these parameterizations. And remember that when we had a parameterization for a curve, we actually kind of forgot the curve itself. We just considered the parameterization to be the curve, right? Even though it was more like just a single expression of the curve. And we also talked about how a curve could have multiple parameterizations. Um, so C1 is the piece of unit circle that goes from pi to 3 pi over 2. So it's this piece, right? So this is C1. And C2 is, of course, the part of unit circle that goes from 0 to pi over 2. So it is this piece, right? So here's C2. Okay, so the two parameterizations, of course, are identical, right? But it definitely matters where the parameter lives. You get two different curves. Now you could say, well, they're really part of the same larger curve where t is allowed to go from 0 to 2 pi, and that's true, but depending on the problem that we're working on, these are, for us, these are totally different curves, right? In fact, these curves don't even touch one another, right? So they definitely cannot be the same curve. So it very much matters where this parameter lives. That's a very important thing. Okay. Similarly, recall a curve can have multiple parameterizations, right? A curve can have multiple, even smooth parameterizations. So I suggest you go back and have a look at the lecture, at some of the lectures on curves to remember what a smooth parameterization is, right? So there was a definition of a smooth curve, which was a curve that had smooth parameterization. Smooth parameterization was one that these component functions were nice enough, and that, remember, there was a big condition here that this r prime of t not be the zero vector for any t in the interior, right? Equivalently, you could require that its length never be 0 for interior points t. I believe you had a question about this on your first exam. Okay, so recall that a curve can have multiple smooth parameterizations, not parameterizations. So an example of another parameterization of C1 is take r sub 3 of t to be the parameterization cosine of 3ti plus sine of 3tj. Okay, where t is, well, this thing we know is actually going 3 times as fast, right? That's the characterization we came up with here. And so what needs to happen here? So to negate that, this window would be pi over 3 to pi over 2, right? Okay. And so you can quickly check that you end up with the exact same values here. So this is the same as C sub 1. It gives you the same curve as R sub 1, even though they're definitely different parameterizations, right? Look, this is cosine of 3t here instead of cosine of t. Okay. So this just gives me C sub 1 here. Okay, now the reason I'm refreshing your memory on how this stuff goes is because the thing that happens for parametric surfaces is very similar. Okay, so what is the idea? Maybe I have enough room to do it here. So as I mentioned last time, if we're sitting in space, you might think of a surface that kind of looks like this, first of all. Right? This is your surface sitting in space, but this surface is nice because it's just the graph of some function of two variables. Okay. So a surface that, of course, is less nice would be something that went passed over or under itself, right? So maybe something like this. So what about like an ellipsoid? Right, some ellipsoid thing. So now this isn't like an open bottom here. This is like this is like some like squished football or something, right? Or of course the easier a more natural example, just a sphere, right? Hold on, my cats are about to fight. Let me break them up. Okay, I think they're fine now. So, anyway, this maybe is the more natural thing you think about when you think about a surface that is not the graph of a function. You see what the problem is. It fails the vertical line test, right? And imagine this line passing from the North Pole to South Pole. That fails the vertical line test. So the upper hemisphere of this sphere is a function of two variables. So here's practice for you. Write out what that function is for a sphere of radius r centered at the origin, we'll say. The bottom hemisphere is another function, is the graph of a function of two variables. But the sphere taken as a whole together is not a graph of a function because it fails the one thing that functions are required to do, which is it has ambiguity here, right? So if I pick the point xy, right, in the xy plane here, I would have two functional values to pick from, and that's not allowed for functions. Okay. And so, how do I get around this? So I hinted last time the way to do it. It's not anything too deep, but the idea of a parametric surface is the following. So to denote a surface, we are going to use the Greek letter sigma. Okay. Sometimes I'll slip and use s instead, so it doesn't matter. That's perfectly fine. But if we want to describe a parametric surface sigma, and maybe our surface looks something like, we'll make it kind of lumpy. So maybe it looks something like this. In fact, why do that when I'm going to pick my favorite type of surface. Okay, so forget this for a second. I could do it here too. I'll just go ahead and do it here. Add in some holes here. So this is like a multi-hole donut. Okay. So it looks something like that. It's the surface of a multi-hole donut, not the filling. All right, so it's just the outside part. Okay, so there's two dimensions here. So here's my surface sigma. How do I describe a point on sigma? Well, a point on sigma, we know, is some point xyz in space, right? So here's another point, here's another point, here's another point. So anything it's going to have three components because it sits in space, so there's three components to list here. What's the best way to describe them? So the best way to describe them is as a vector-valued thing, okay, but different than our normal vector-valued functions, which take in one parameter and spit out a vector, either in the plane or in space. This is a vector-valued quantity that takes in two parameters. So I have, maybe I'll write it down here to give myself room. So I have a parameterization R. I have parameters UV, and this is X of UVI plus Y of UVJ plus Z of UVK, where U and V, those parameters, you have to tell me where they live. Now, you can't separately say U lives in some in some interval and V lives in some interval, because then UV would be like a rectangle, and that's not general enough. So UV lives in some R, right? Some set R, where R is a set in the UV plane, right? Where R is some set in the UV plane. Okay. So let's think about this for a second. Okay. Now, let me bring back my previous drawing here, what we did for curves. Okay, so first of all, what was one of the trickiest thing about dealing with a parametric curve versus thinking of it as a function? Kind of the trickiest thing that students have a hard time getting over is this parameter t, where is it? Right? So this is the x-axis, this is the y-axis, but where's t? Well, there is no t-axis, right? That's actually kind of the point, is that this parameter t lives in a part of, it lives in some interval that we don't actually physically see here in the drawing, right? So similarly, the exact same thing is going to happen here. For this parametric surface, the parameters u and v in the set they live in are, you're not going to see it here because this is the x, y, z space, right? And you're not going to see this r. So this r is not like the shadow of this thing, okay? And that can be a little bit confusing. Maybe even I could use a different letter here, okay, to do that. I'm not going to. I'm just going to keep to the notation that the textbook uses so that if you're looking at the textbook, you don't get confused. But this R is not like the region R that we've been dealing with in the last couple of chapters, where that was taken to be, if you thought about flashlight shining from the positive z direction, it's the shadow that it casts on the xy plane. That's not going to be what this R is. Okay. In fact, this R in a lot of cases is going to be the entire UV plane. U and V are just going to be allowed to be whatever kind of real numbers that you want them to be, right? So they're just allowed to be reals. And sometimes this R is going to be a specific region in the UV plane. Okay. And we'll see what I'm talking about there when we do a couple of examples. So that's the first thing. Okay. So, so maybe I'll write that down, right? So, here's some notes. All right, so one, you can't see U and V, and thus R, when you draw the surface sigma. But this isn't anything that's specific to parametric surfaces. This is actually something that was also true for parametric curves. You couldn't see t. Okay. Okay, so what's next? So intuitively, when we have we'll call it a parametric object. Now, I'm not going to deal with any kind of parametric object other than curves and surfaces, but that's just because that's what this course calls for. But you might have guessed by now that you could keep doing this. You could talk about a parametric space. You could talk about a parametric hyperspace. You could talk about a parametric five-dimensional object. Okay, and so there's nothing that keeps you from just doing this forever by increasing the number of parameters. But intuitively, when we have a parametric object, so that for us means curves or surfaces. But like I said, you can actually keep doing this. The number of parameters tells you the dimension of the object. So what do I mean by that? All right, let's go back to a curve. Okay, so for a curve, we have one parameter describing this curve, and that tells you that a curve is one-dimensional, right? Now you might say, curve is one-dimensional. What do you mean? Well, this curve sits in the plane. The plane is two-dimensional, of course, but a curve is one-dimensional. What does that mean? Well, intuitively, it means there's one axis of motion. There's one direction that you can move in, right? And so we can actually see that direction here at this point, right? So if it helps you, we can consider the line tangent. This gives us a line, and, a line that is, it's a line, not a curve. This gives us a line, and on this line, we can go in two directions. We can either go in this way or this way. Right? But we actually don't think about those as two different directions, right? We think about them as lying on the same axis of direction. So If I go this way some amount, well, that's the same as going minus that way. As far as motion goes, we don't consider this a different direction, right? So a way to talk about that in vectors, right, is that any tangent vector here is a multiple of some other tangent vector there, right? And so they are parallel in that sense. And so this is one direction, right? This is one dimension's worth of direction. And even without this, you have a point here, right? Think about this as a particle tracing out some trajectory. There's only one way you can go, right? So you have one direction. You can either be going this way, you can be going the other way, but we don't count that as a different direction. That's just the same direction, just in the minus. This is just minus whatever you're doing going in this way. Okay, so that's one dimensions worth. So even though it sits in the plane, it's a one-dimensional object, right? So it sits in two-dimensional space, but it's a one-dimensional object. Same thing is true for a curve in space. A curve in space sits in a three-dimensional space, but it's a one-dimensional object, right? I got two ways I can go. And of course that meshes with the fact that I have one parameter describing this. So it's a one-dimensional thing. So similarly, okay, on a surface, well, now I have two parameters describing it. So even though my surface sits in three space, right, it's not a three-dimensional object, it's a two-dimensional object. Why? Because there's only two directions I can go in. So at a point here, I could go in this direction or minus that direction. So that's one dimension's worth of directions. Or I can go in this direction. Now you could say, wait, do you have to go perpendicular, right? Could you go like in this direction, and does this count as a different direction? Yes, it does. Anything that's not parallel to that. But once you pick two vectors and they're not parallel, that gives you the rest. That gives you the plane's worth of directions at that point. But you only get two, right? Because remember, this is a surface. You can't go into this thing. You can only imagine a ball, right? Or not a ball, but imagine a sphere. I thought I had a cat toy sphere. Let me try to find it. Oh, yeah, I have something. Okay. Here's a small sphere. Okay. So don't think about this ball as having an inside. Imagine you're like a little insect here, and your feet, you're wearing like, this is metal, and you're wearing like magnetic boots or something, right? So you can only slide your feet along this. You can't jump, you can't burrow into this thing. You're stuck on the surface of it, okay? Now you can walk around it though. So you could go this way. You could go some other way that's not parallel to that way. But once you specify that, you get all of the directions that you could go in here, and that is two dimensions worth. So once you've chosen vectors that are not parallel, right, like that are transverse to each other, then that gives you everything. Those two vectors are what are called linearly independent, and they span a two-dimensional set. Okay, so that two-dimensional set is your directions, right? So if you think about it, you could have a plane that is exactly tangent to this sphere at that point, and that plane, of course, is two-dimensional. All right, so I need these two parameters to describe a two-dimensional object. The reason I went through all that hassle to say this is because you're going to be asked to parameterize surfaces, and if you wonder like what info you need to do that, well, if it's a surface, you need two parameters to describe that. If your description relies on less parameters than that, you cannot possibly do it. You don't have enough dimensions worth of parameters to describe the thing. Okay, and the other thing I want you to note is R of UV is a vector valued function of two variables. right? So this is something that we haven't really talked about. All of the vector valued functions we did in chapter 12 they were even defined to be functions of one variable, t, right? Here, we have a vector valued function, but it's a vector valued function of more than one variable. This is usually why I wait to do this until chapter 15, because first thing we're going to do in chapter 15 is talk about the notion of a vector field, which is basically a vector valued function of several variables. So it's exactly the same sort of thing that this thing is. Okay, and so that's one of the reasons why I wait to do this. The other reason is because all of this stuff we're doing right now is stuff we're not going to use immediately, but we're going to use it like right at the very end of the course. Okay. Okay. So let's do some examples. So let's see. That's my first example here. So find a parameterization of the sphere sigma, which is given by the equation x squared plus y squared plus z squared is equal to 4. Okay, so we draw a picture here. We have a sphere. We note that we cannot describe this as the graph of a function of two variables. Okay. Of course, this point here on the y-axis would be 2. This point here on the x-axis would be 2, because this is a sphere of radius 2, right? Okay. And so, how do I do this? Well, here's where my thing that I noted comes in. So intuitively, when I have a parametric object, like I want to parameterize this sphere, the number of parameters tells you the dimension of the object. Well, a sphere has how many dimensions? Well, it's two-dimensional. So I know that whatever description I come up with, I'm going to have two parameters. Okay. So you see a sphere. What is kind of the best way to describe a sphere? Well, what about spherical coordinates? All right, that's kind of our first idea here. What about spherical coordinates? So spherical coordinates, in spherical coordinates, how would I write the equation for this sphere? So in spherical coordinates, what is this sphere? This is the sphere rho is equal to 2, right? Okay. Well, that in itself doesn't help me that much, but let's maybe write out in spherical coordinates what specifically how this sphere would be described. So if we actually write out the form that spherical coordinates takes, right? So x is equal to rho sine phi cosine theta, and y is rho sine phi sine theta, and z is rho cosine phi. Right? Okay. Well, if at every point on this sphere, rho is equal to 2, right? So really, this is 2 sine phi cosine theta, and this is 2 sine phi sine theta, and this is 2 cosine phi. Oh, but we did it, right? So our parameterized sphere is r of phi theta, which is the x slot is 2 sine phi cosine theta, I, plus 2 sine phi sine theta, j, plus 2 cosine phi, k. Now we're not totally done because we need to know where phi and theta live. Okay. So where does phi live? Well, phi needs to describe this entire sphere. So it is, remember, phi's measured from the positive z-axis. Theta takes care of the around, so don't get confused here, right? The maximum range of phi is 0 to pi, and so that's exactly where phi lives. And theta is around the entire sphere, so this is 0 to 2 pi. Okay. And so a single point here on this sphere is r of phi theta. It's determined by these two parameter values. What would r be in this case? R would be a rectangle, right? It'd be a rectangle of length pi and height 2 pi, right? So this is what r is. Okay, so in this case, r is pretty simple. All right, so there's our parameterization of the sphere. All right, so think about it for a second. So to test this, if you're ever curious as to whether or not the parameterization you found is the correct one, so just test in your mind, is it enough to specify both a phi and a theta to pick out any point on the sphere? So here's my sphere. Here's the North Pole. South Pole is directly on the opposite side. So let's say I take the point here, right? How do I describe that? So we'll say my x-axis is coming out of the sphere like here. Okay, I have a point here. How do I describe that? Well, I would go down phi and around theta. And there it is, right? And you can do that with any point, right? So any point is determined by how far down the sphere it is, that's phi, and how far around the sphere it is, measuring from the positive x-axis, that's theta. Okay, so yeah, indeed, this does it. Okay. Jacob, phi is from 0 to pi because theta takes care of the around, right? So there's phi takes you for either from the top or the bottom. That's all it's saying. Theta is telling you how far around the thing is. And since theta runs from 0 to 2 pi, it takes care of everything, right? So an easier way to look at this, if you don't believe that phi only needs to go from 0 to pi, try to find a point on the sphere that you couldn't describe if phi, so let phi be between 0 and pi, let theta be between 0 and 2 pi. Try to find a point on the sphere that you can't get to, right, because phi can't go beyond pi, right? When phi is equal to pi, right, when phi is equal to pi, what point do you get? You get the South Pole. When phi is equal to 0, you get the North Pole. Right? When phi is equal to something in between, well, you need some theta to tell you what point around the circle you get. So typically you're getting a, you know, some circle around that sphere. Sorry. All right. Yeah. So try to find a point on the sphere that is not describable with phi going from 0 to pi. Right. Okay. So, next example. Let's see here. Yeah, so let's find a parameterization for the part of the double cone x squared plus y squared is equal to 3z squared, such that z is greater than or equal to 0. So this is the upper nap of the cone. Okay, it is a cone, so again, the idea here is to use spherical coordinates. Okay. Now, what do we know about cones? Cones have a very simple description in spherical coordinates. They're described as phi is equal to alpha for some angular value alpha, where the alpha is whatever this is, right? Okay. Okay. And so, what do I need here? Well, let's look at this particular expression in spherical coordinates. What does this become? this becomes, so x squared plus y squared is r squared, and that's equal to 3z squared. But then using spherical coordinates, this is rho sine phi squared is equal to 3 times rho cosine phi squared. Right? And so dividing through by rho and cosine squared phi here, I get that tan squared phi is equal to 3, so that tan phi is equal to root 3. This is the upper nap of the cone. So this phi must be, if the tan phi is root 3, what must phi be? Phi must be pi over 3. Okay, and so in spherical coordinates, this cone is describable as phi is equal to pi over 3. Now, how do I make use of that for spherical coordinates? Well, it means that pi over 3 is specified here, right? So again, we use spherical coordinates. So the x is rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. But this phi is determined for any point on this cone, right? And so plugging that in, so I'm plugging phi equals pi over 3 in here, so I get rho sine pi over 3 times cosine theta. And here I get rho sine pi over 3 times cosine theta. And here I get rho times cosine of pi over 3. Okay, but what's sine pi over 3? Well, that's root 3 over 2. So this is root 3 over 2 times rho cosine theta. And this is root 3 over 2 times rho. Oh, sorry, this is sine. Okay, so this is rho sine theta. And this is root 3 over 2 times rho. And so I have my x, y, and z totally describable in terms of two parameters, rho and theta. And so my parameterization is r of rho theta, which is root 3 over 2 rho cosine theta I, plus root 3 over 2 rho sine theta j, plus root 3 over 2 rho k. All right. And now I have to determine where my rho and theta live. So we're going all the way around the cone here, right? Measure from the positive x-axis. So theta is between 0 and 2 pi. And rho is, this cone is an infinite surface, right? It's infinitely going up here, up and out. And so rho is just greater than or equal to 0. Or if you want to view it as being in some interval, it's in this interval from, it's closed at 0 and then open at infinity, right? But this is a perfectly fine way of describing it. So there we go. There's our parameterization. Okay. Oh, yes. Yeah. Why did I do that? Here. This is not root 3 over 2. This is 1/2. Yes. Yeah. Copying myself too much. This is 1/2. There we go. The chat corrected me. Okay. All right, so that's how this works. All right. Again, right, we have two parameters here. This is a good way of getting you to think about these parameters u and v. I mean, you're using u and v because those are your dummy values, but those parameters may actually show up in some other way. So let's do another example. So how about we find a parameterization for the cylinder x squared plus y squared is equal to 4. Okay. So what does this cylinder look like? This is an infinite cylinder. X squared plus y squared is equal to 4. I have a cylinder that looks like this. Right, maybe here. So this is just one that's centered on the z-axis. We could do this exact same thing for a cylinder that's centered on the x-axis or the y-axis, right? So consider the cylinder x squared plus z squared, right, is equal to 4, right? That would be a cylinder that is centered on the y-axis. Or y squared plus z squared is equal to 4. That would be a cylinder centered on the x-axis, okay? So we could do this regardless, all right? So now we're just thinking here for a second. Okay, so intuitively, right, before I even write anything down, so now we're using the power of intuition here to come up with how we would describe where we are in the cylinder. Of course, I've drawn the cylinder with ends. This is an infinite cylinder, so it's actually going on, in both directions, so it doesn't end there. I've just done that to show you that it is indeed a cylinder. Okay, so how would I describe a point here? So if I were thinking about, how I would describe to someone where I am on this infinite cylinder, so I have the origin as a reference point, right? So I would say, okay, well, I'm either up or down the cylinder relative to some z level, but that's not enough, of course. If I tell people that I'm, say, 5 meters up this cylinder, right? That's not enough. I could be at any of these points. I need to specify a single one. So what would I do? I would come 5 meters up the cylinder, and here, along this circle that's determined by cutting off, right, a cross section at 5 meters up, I would need to tell how far around the circle I am. So that tells you right there, what are the 2 parameters you think you're going to need? Well, a height, that's given by z, and how far around the circle you are, which is given by theta. So you should be able to figure this out just from that you're going to need a z and a theta here, right? So z and theta is our idea. So how are we actually going to do that? Well, this circle, if I bring this circle down to the xy plane, what is that circle? Right, this is the circle, x squared plus y squared is equal to 4 in the xy plane. If I write out how to describe x and y in terms of that circle, well, this would be 2 cosine theta, and y would be 2 sine theta. That describes going around this circle at the height z equals 0. Okay, and so what is my idea for how to parameterize this? I need 2 quantities, z and theta, or theta and z, however you want to, which order you want to put this in. This would be 2 cosine theta I plus 2 sine theta j plus z k, where z is a real number, right? It can be anything, and theta is between 0 and 2 pi. So there's my cylinder. In the chat, someone asked, will there be any more exams before the final exam? Yes, you will have an exam next week. I will post an exam at some point. So yeah, sometime next week I'll post your 3rd exam, and then that will be the last exam you have until the final exam, final exam will be cumulative, so it'll cover everything. Okay. Let's see here. Finals are like May, like second week of May, I think. So yeah. So you'll have an exam 3 next week that covers this stuff, and then you'll have a final exam a couple weeks after that. Okay. So what other examples can we cook up? So one thing that was nice is going back here. So going back to the plane, when I had a curve that I could describe parametrically if I wanted to, but actually turned out to be nice, right? It turned out to be the graph of a function. Well, this had a very easy parameterization. How did I parameterize this as a curve? If this was the graph of a function, say f of x, then my parameterization was easy. My parameterization was ti plus f of tj, right, where t is in a to b. So when you had a curve that was actually the graph of a function, the parameterization was easy. Okay, so what if we have a surface that we want to parameterize, but actually it's nice. It is the graph of a function f of xy. Is there a similarly easy parameterization? Yes. R of xy is xi plus yj plus f of xy k, right, where if this is R, xy is in R. Aha! All right. So this is the rationale behind using R here, because sometimes when you're lucky, the surface that you're parameterizing is actually the graph of function two variables. Okay. All right. So, quick example. Give a parameterization for the circular paraboloid z is equal to 4 minus x squared minus y squared. Well, the answer is what? My parameterization. I have parameters x and y. This is just xi plus yj plus 4 minus x squared minus y squared k, where x and y are in R, where R is the closed circular disk of radius 2. Right? Oh, actually, I didn't say that it was the region above this, so actually R is just the entire plane. Right? I was going to include that description, but I jumped the gun. So R is the entire plane. So if you like it, this is just R2. Okay. All right. This is important that you note this because if you don't have an easy way of describing surfaces that arise as graphs of functions of two variables, then it would be kind of annoying to do this whole parametric thing. But because now all of the stuff you did sits inside this parametric surface stuff, right, then you could just always use this. So whatever computation we come up with that arises out of this, you could always apply it to the surfaces that you saw from the earlier chapters. Okay, that's the nice thing. And it turns out that in a lot of cases, the stuff that we're going to be doing it on these kinds of surfaces anyway. So it's important that we have a quick way of doing this. Okay. All right. So, what else? What are some other examples? So, we also have the example of, let's say we're going back to our question of curve in the plane. We'll say that this is describable as, so this point here would be the point x, f of x. So this is the graph of some function of x here. And this is A and this is B. Okay. Do you remember in Calc 2, or depending on where you saw this, you could have seen it in Calc AB, I guess. The notion of a surface of revolution. So what was the notion of a surface of revolution? The idea is that you took this graph and you rotated it, say either around the x-axis, you rotated it out of the paper around the x-axis to sweep out a surface in space, or maybe you rotated it around the y-axis to sweep out a surface in space. But the way that I've drawn this, we're going to sweep it about the x-axis here. Well, what are you doing when you do that? You are considering me having a z-axis, right? Like this pin sticking out of the paper. You're sweeping this surface out. Okay, when you do that sweeping, what happens to, say, this line? What does that line sweep out? Well, it sweeps out a circle or a circular disk, but it sweeps out a circle. Okay, and so what is the radius of the circle that it sweeps out? Well, this height is determined by the height or the value of the function at a point x, right? Okay, and so how do we parameterize the surface of revolution? So if this is sweeping out that circle, then in the y and z directions, so x, to describe a point on this surface, x tells me how far along the surface I am between A and B. So x is just x. That's good enough. Y is involved in this circle that's being swept out. Okay, so in fact, y and z are described as a circle of radius f of x, and I'm sweeping out 2 pi worth of angle here, so y is f of x cosine theta, and z is f of x sine theta. And so, to parameterize my surface of revolution, I have 2 parameters, x, which is how far along the surface I am, theta tells me how far around the surface I am, and this is given as xi plus f of x cosine theta j plus f of x sine theta k. Okay, where, of course, we have to say x lives between a and b, and theta is from 0 to 2 pi. So, hey, now you have a full way of parametrically describing those surfaces of revolution that were introduced to you forever ago, right? So now you can actually compute other things about those surfaces rather than just their volume, right? Okay, one more thing, and then I'll be done, and then I'll answer some of these questions that are in chat. So one more thing. The helicoid that I mentioned last time. If you want to see a parameterization of this helicoid, so this was this weird circular ramp thing that I drew at the end of lecture last time. So what is that? The helicoid is, it has parameterization r of uv, which is u cosine vi plus u sine vj plus vk, where u is the cutoff, so you can make u whatever you want. I'm going to make it between 1 and 2. And v is, if you want 2 rounds, so v is from 0 to 4 pi, if you want to go around twice. So this is, as promised, that weird, crazy surface, the helicoid, can be parameterized in this simple way. Okay. So next time I'm going to talk about the notion of a smooth surface, then I'm going to get into talking about cool things like Klein bottles and stuff, and then I'm going to give away for computing surface area, and then we will move on to chapter 15. So that's the plan. Let's see here. So is the final same format as our previous exams? Yes, it is, but you'll have like less time to do it. You'll have like a day or two to do it. So I'll post it on the day that we're scheduled for finals, which is the first day of finals. So on the first day of finals, I'll post your final exam, and you'll have like 1 to 2 days to do it. So yeah, to answer both of those questions, is the final going to be take home? Yeah, it's going to be the same format as the rest of the exams were. Okay, just on a quicker turnaround. Ethan, yeah, when's the MATLAB supposed to be due? Tonight? Yeah, I can send a reminder to everybody about the MATLAB and post your second MATLAB assignment as well. So I can't remember when did I make the MATLAB due? Today? I think so. I think I made it due today. Yeah. So I'll send a reminder to everybody so that there's no stragglers left behind. All right. So anyway, that's that. I will see you all on Monday.